Hello everyone, thanks for joining in. Today we will understand BGP path attribute topic. So as we know that this is the most important topic of BGP and in all interview maximum question to be asked from this topic. Okay, so let's start. So here, what is path attributes in BGP? So BGP path attributes are those criterias which are used by BGP to define its best path. Similarly, we use in OSPF and EIGRP, we use metric, right? So in OSPF, the metric is bandwidth that is used to define the best path. And in EIGRP, we use five metrics like bandwidth, load, delay, reliability, and MTU. Similarly, in BGP, we have path attributes. With the help of this, we define the best path, right? So here, path attributes divided into two criteria. First one is well known, and second one is optional. So, well known as the name suggests that BGP attributes will always go along with BGP updates. Okay, and optional attributes will never go along with BGP updates until and unless we configure. So here, well-known attributes is divided further into two categories. First one is mandatory and second one is discretionary. And optional attribute is also divided into two categories. First one is transitive and second one is non-transitive. So what is mandatory? Mandatory attributes will always go in BGP updates and discretionary attributes are those that sometimes BGP take them in its updates and sometimes not. So we can understand here, so which attributes comes under mandatory and which attribute comes under discretionary. So here we have a list like origin code, AS path, and nest hop reachability comes under well-known mandatory attribute, and local preference and atomic aggregate will come under well-known discretionary. So we will understand in next few minutes why sometimes BGP take them in their updates and sometimes not, right? So our next attribute, or we can say next criteria is transitive attribute. So if router receives any updates and it does not support attribute, then it removes the attribute and forward the prefixes to their neighbor. So in transitive here we can see aggregator and community attribute comes under optional transitive. So here aggregator and atomic aggregate attributes comes in the picture when we will perform the aggregation. Aggregation means summarization. So if we will not summarize the networks in our BGP, then two attributes will not come in picture. So that's why we have written here that if a router receives any updates and it does not support attribute, then it removes the attribute and forward the prefixes to its neighbor. And in non-transitive, if router receives any updates but it does not support attribute, then it discards its update. So here we can see in non-transitive attribute MED multi-exit originator ID and cluster list. These three attribute comes under optional non-transitive. So here originator ID and cluster list attribute comes in the picture when we will configure route reflector in BGP. So if this is not configured, then these two attributes will not come in picture. So that's why here written that if router receives any updates but it does not support attribute, then it discard its update. And here we have one more attribute that is med. So actually med we use in BGP when we redistribute other protocols in BGP. So they are metric like OSPF, as I said that in OSPF we have metric called bandwidth, right? So when we will redistribute OSPF in BGP, then their metric will be come in BGP in the form of MED, right? So here we have few path selection criteria in BGP, and we need to memorize this, right? So this is the 11 BGP path selection criteria. So first one is nest hop reachability, second weight. So we will understand one by one in detail. Third one is local preference. Fourth, AS path length. Fifth one is origin code. Sixth one is multi-exit discriminator. Seventh one is eBGP preferred over iBGP. Eighth one is IGP metric. So here IGP cost to reach next hoop. Ninth one is oldest path. It's for only eBGP neighbors. Tenth one is lower router ID of neighbor, and it is only for IBGP neighbor, and lower neighbor IP address. This is also for only IBGP neighbors. Okay, so let's understand the first one, that is nest hop reachability. So nest hop must be reachable, otherwise will not make the best path. So here, if nest hop is not reachable, then router will not move on another path attributes. So let's understand with the topic. Suppose R1 receiving the prefixes from R2 and the R2 is not reachable, then that prefixes will be there in its BGP table only, will not be moved to routing table. So if nest hop is not reachable, then this router or BGP will not move on the next path selection criteria, and that prefixes will not be best in BGP, right? So this is the first criteria, that your nest hop should be reachable for BGP, okay, for a BGP update. Now, second criteria is weight. So it is locally significance. That means BGP will never carry with its update. If you have configured weight in one router, so that weight will be apply only on this router, will not be apply on all the routers present in a single AS. Okay, and it's Cisco proprietary. So for self-advertised prefixes, it is by default 32768. That means if we have router 1 and we are advertising prefixes from router 1, then for that prefixes weight will be 32768, and for all the received prefixes, either we are receiving from eBGP or IBGP, its by default value will be 0, and higher weight will be always preferred. Okay, now suppose R1 is receiving prefixes from R2 and R3, or we can say we are receiving the same prefixes from R2 and R3, right? So as I said that for all the received prefixes, weight will be by default 0. So here we cannot define that we should make R2 path will be best or R3 path will be best, right? So we need to check the another path selection criteria, that is local preference. So for local preference, we need to keep in mind that BGP will always include local preference attributes in outgoing BGP updates, but only for IBGP neighbors, not for eBGP neighbors. Okay. So by default, local preference value is 100 for internal prefixes. Internal prefixes means IBGP prefixes, and the higher value will be always preferred. So local preference, as I said, that never goes across the AS. Across the AS means it will never go for eBGP neighbor. Okay. So for self-advertised and external prefixes, its value is null. Null means nothing. Okay. Here we can say that within AS, local preference will play a vital role for best path selection. So that's why here we have written, let me show you, that sometimes BGP take them in its update and sometimes not. So here discretionary, we can see that local preference comes under well-known discretionary. So that's why we have written that sometimes it will take them and sometimes not. So for eBGP neighbor, LP will never go for eBGP neighbor, only for IBGP neighbor, right? So I hope you folks understand. So here suppose we have R1, R2 and R3, there we have three routers. So we have eBGP neighborship between R1 and R2 and IBGP neighbors between R1 and R3. So here we will not compare that. Suppose we are receiving the same prefixes from R2 and R3, so we will not compare here that which path will be best. So because local preference will work only for internal prefixes or IBGP, not for eBGP. Okay, so here we have written that local preference will never be compared in this scenario. So it will be used for, so here it will not be used for best path selection. Now if we have this topology, let me show you, like this topology, right? R1, R2 and R3, and we are receiving the same prefixes from R2 and R3. Okay, so as I said that for internal prefixes local preference value will be 100, right? So here we cannot decide that which path will be best, so we will move on another criteria, that is self advertised. Okay, now let's suppose that we have one topology, and in that topology we have only two routers, R1 and R2. Okay, so here R1 is advertising the same prefixes and the same prefixes is receiving from R2. Okay, then R1 will make it best of the self advertised prefixes only. It will not make the best prefix that is receiving from R2. Okay, so that we need to keep in mind. In multiple scenario you will see, and I'll show you as well in our upcoming practical part. Okay, so here we have written that if R1 is advertising the prefixes 100.100.100.0/24 and also receiving the same prefixes from R2, then it will make the best of self-advertised prefixes. Now let's suppose that we have like this scenario, R1 and R2 and R3, and we have IBGP neighborship between R1 and R2 and R1 and R3, and we are receiving the same prefixes from R2 and R3 as well. So here with the help of self-advertised or local preference, we cannot decide that which path will be best, right? So we need to keep move on the next path selection criteria, that is AS path. So AS path we use for eBGP neighbors only. Okay, so we'll see how we can decide that which path will be best in IBGP only. So we'll come in next few minutes. Okay, so we need to follow only this steps or this path selection criteria. We need to move on step by step. We cannot jump from next hop reachability to eBGP over IBGP. We need to keep move on step by step. Okay, we need to see all those criteria, if it is tiebreaker or not. If it is not, then we need to move on next to path selection criteria. If it is not, then we need to move on next path selection criteria. Okay, so that's why we are moving step by step. So our next path selection criteria is AS path, so autonomous system path. So BGP can put 64 AS path in its AS path list. Okay, so here we suppose we have four routers, R1, R2, R3 and R4, and we have eBGP neighborship between all these routers, like R1 is in AS1, R2 is in AS2, R3 is in AS3 and R4 is in AS4. So suppose R1 is receiving the prefixes from R4 40.40.40.40. So here we can see that via R2 it's crossing the two AS, right? AS2 and AS4, and via R3 as well it's crossing the two AS3 and AS4. So we cannot decide here that which path will be best, right? So if this is with the help of AS path we are not able to decide the best path, then we will move on next path selection criteria, that is origin code. So we have three different types of origin code. First one is I, second one is E, and third one is question mark. So here I means IGP, and in BGP actually this IGP represents BGP. Okay, so here suppose we have this network R1, R2, R3 and R4. If we are advertising our prefixes from R1 with the network command, okay, then that prefixes will be show with I origin code. Okay, and I means here EGP that was used before BGP, so we will not see in our network, so we can ignore this part. And here question mark represents incomplete. Incomplete means redistribute. So when we will redistribute any other protocols like EIGRP or OSPF in BGP, then this question mark we will see. So here we have written here that in origin code IGP means BGP, that we have already said. So if we are advertising any prefixes within network command, by default the origin code will be I. Okay, and E means EGP. Now we are not using anywhere in production network. Production network means in our network, running network. And if we will redistribute anything in BGP, then origin code will be question mark. Everything that I'm saying here we will show you during the practical part. Okay, and here I will be preferred over E and E will be preferred over question mark. Okay, now we have suppose this topology R1 R2 R3 and R4. Okay, and R4 is advertising this prefix via network command. Okay, then in R1 this prefix will be reflect as I, right? So here we cannot decide that which path will be best via R2 or via R3, right? So we will move on our next path selection criteria, that is med means multi exit discriminator, or we can say metric. Okay, so mid is always by default 0 and lower value will always be preferred. So it's similar to IGP metric, and we already said before that when we redistribute any protocol OSPF or EIGRP in BGP, then its metric goes in the form of mid in BGP update, and we will see in detail all the path attributes in our practical part. So there will be a fun. Okay, so I think it will take around 1 to 2 lectures more for theoretical part. After that we will do only practical part. Okay, now suppose it's not able to decide that which path will be best, then we will move on another path selection criteria, that is external over internal. Okay, now suppose we have this scenario R1 R2 and R3, and between R1 and R2 we have IBGP neighborship, and between R1 and R3 we have EBGP neighborship, and we are receiving the same prefixes from R2 and R3 both. Okay, then here as per the path selection criteria, external over internal, that means EBGP will be preferred over IBGP. Okay, so R3 path will be preferred over R2. Now our suppose before moving this, suppose we have EBGP neighborship with R1. Okay, so we cannot decide here, right, that which path will be best. Then we'll have to move on another path selection criteria, that is IGP cost to reach next hop. So in our practical part we will see that sometimes we configure IGP in the background of BGP. Okay, so there we will compare IGP cost with the BGP. Okay, now suppose this path selection criteria is also not able to decide that which path will be best, then we will check the oldest path. Okay, now suppose we have scenario like R1 and R2 and R3, we have three routers and EBGP neighborship between R1 and R2 and between R1 and R3. Now suppose R1 has received the prefixes from R2 first, and later the same prefix is receiving via R3. So R1 will make it best via R2 because it receives before than R3. Okay, so here we have written that, let's suppose no IGP is configured on the background of BGP. Okay, so we will check the oldest path. Okay, so for EBGP neighbors only the oldest path will be preferred. Okay, now suppose here we said that we have this scenario IBGP IGP, and we are not able to decide with the help of local preference and self advertise that which path will be best, right? So we have one more criteria, or we can say tiebreaker, that we can compare with lower router ID. So we have this topology. Let me copy here, and no, not this one, IBGP IGP. Okay, and paste here. Suppose we have this scenario R1 R2 and R3 and R4, all four routers are in same network, or we have IBGP neighborship. Okay, so here R1 is receiving the prefixes from R4, right? And now let's suppose the router ID of R2 is 2.2.2.2, and the router ID of R3 is 3.3.3.3. Okay, so here the router which has lower router ID, that path will be best. So lower, so here this one is also a tiebreaker. So here R1 will put R2 as the best path in place of R3. Okay, so in multiple scenario you will see that we have the same router ID for its neighbor. Like this scenario, suppose we have this scenario R1 and R2, and we have two links between these two routers, okay, and we are running IBGP, okay. So how can we decide that which path will be best, because we are receiving the same prefixes from both the link? So here we will decide with the help of lower neighbor address, okay. So here we have written that it's also possible we have same router ID of IBGP neighbors, right? So here one more thing we need to keep in mind, that BGP does not support equal cost load balancing, because by default maximum path configured is 1 in BGP, okay. So BGP will perform load balancing when all attribute will up to IGP cost to reach next hop is same. So here we have written all those criteria. If from next hop reachability to eighth number IGP cost to reach next hop, if all those criteria are not able to decide that which path will be best, then it will perform equal load balancing, okay. So folks, this was the topic for today, okay. So I hope you have learned something new. Till the next video, I am signing off. Take care.